Hello, good evening. I will be discussing today our research work, which is related to the scaling of GMM expectation maximization algorithm, which is one of the most prominent algorithm in the machine learning domain. And we have used the BSP approach, the bulk synchronous parallel approach, which is provided by the Apache Hammer. So we'll discuss our implementation, and we have done compared it with different other implementations by using different cluster computing, the general purpose cluster computing frameworks like Apache Hadoop and the Apache Spark. So let me just give you kind of a brief overview about the EM algorithm. The expectation maximization algorithm has been invented in 1970s by the Dempster et al. And this algorithm gives the maximum likelihood estimation parameters when some of the data set is missing. The GMM is one of the special case where we can definitely use the EM algorithm, where we can see the underlying data as a mixture of different Gaussian models, and the purpose can be a clustering of the data where we can separate these different Gaussian mixtures from each other. And I see this is most widely used nature of the EM algorithm. This is iterative in nature. The algorithm has the expectation as well as maximization steps, which and there are lots of such iterations need to be done. And after the iterations, it gives the kind of guaranteed convergence after some number of iterations. The algorithm is used into the different contexts, like it used in the machine learning in the form of clustering the data sets. It used in different fields like computational biology, computer vision, and many other fields. Start with one of the cluster computing framework that we have considered, which is a MapReduce, and it's simply the Apache Hadoop as the MapReduce implementation. This is widely used the cluster computing framework, and it has the implementation of the expectation maximization algorithm. So we have considered the standard implementation provided by Apache Hadoop. In Apache Hadoop, it has a kind of there is a machine learning library built over the Apache Hadoop called as a Mahout, Apache Mahout, and we have considered the implementation of EM from the Apache Mahout. So basically, the Hadoop is mostly used in the data intensive kind of workloads where we can write a map and reduce tasks, and these tasks run on the different clusters so that we can do the things in parallel. The data resides into a Hadoop distributed file system in the form of the data blocks, and each map task can work on the certain number of can take the input from the certain data blocks, and then we can have a kind of shuffle and sort phase where we can have uh, the data transfer between the different nodes in this space, and we can have a reduced space where we can do a kind of reduce operations. So in case of EM algorithm, we need to do a lots of map reduce jobs, because for each iteration we need to do a kind of one map reduce task, and starting a kind of map reduce job is itself a time consuming. So for the iterative algorithm, map reduce is not that suitable. So let's start with the BSP framework where which we have used for in our implementation. So basically, Apache Hammer is a general purpose BSP framework. It gives a lots of imperatives or function calls which we can use to perform a BSP like programming. So we can so in BSP we do have a notion of super step. So one super step consists of some kind of local computations by each and every node. Then comes the kind of communication phase where we need to transfer data between different nodes, and then we have to do a kind of barrier synchronization step where we can certainly say that the sync has happened and all nodes have a kind of attained a particular state. So we can have a multiple super step, and we can write a super step in Apache Hammer. So we'll see how we have converted the EM algorithm using the Apache HAMA ladder. This is a very upcoming framework called as Apache Spark. It has a concept of RDD, which is called as a resilient distributed dataset, which gives a distributed abstraction of memory. And I think that's the basic concept behind Spark becoming a popular, because RDDs are immutable and we can do a different operations on the RDDs. We can have a distributed abstraction of memory, so most of the things can be in memory, and it takes a very good advantage of the memory of the cluster. And so that's, and again the fault tolerant is also handled inside the Spark, so it is suitable, definitely suitable for iterative and interactive kind of workloads. And in case of expectation maximization, we have a iterative workload, so the Spark framework is also suitable. So that's why we have considered is the implementation of EM in Apache Spark as one of the comparison with our standard Apache implementation. Let's start with the GM algorithm. How I will quickly introduce you how it will work in the context of the GMM, the Gaussian mixture model. So on the right hand side, let's see this. You can see this different number of clusters inside the data. So for this algorithm, we have to do the give the number of clusters a priori. How many clusters we have to find inside the data. So let's see, this is a two-dimensional data set where we have x and y value as the coordinates, and you can see there are three clusters. Visually, you can see there are three clusters. So let's see, if we give the algorithm to find out the three clusters, then how it does that. So basically, we have these two attributes x and y, and we do have some statistical parameters as mean and standard deviation for each and every cluster, for each and every attribute. And these parameters we don't know a priori. So let's say we have some kind of statistical parameters because we don't know the clusters a priori. So we have taken this randomly. So let's start with some random statistical model. I will say this is a statistical model for this data. So we have to find three clusters for each and every cluster. Let's start with some random mean and standard deviation values for each and every instances. So we do have a 15 instances which needs to be clustered. So these attributes needs to be found after by our algorithm. So in the expectation step, what the algorithm does is that it, for each and every instance, it will use this model as the input, and by using this model, it will assign some kind of the probabilities for each and every cluster for this instance. So let's say for 1 and 1, it can give a very higher probability for the cluster 1 and some probabilities for cluster 2 and cluster 3. So as we started with the random, we'll get some data here. So we can use this data and maximize the probability, and in this way we'll do a kind of maximization step on the after the expectation step, and we can then find out these, modify these parameters accordingly to the updated cluster instances. So we are using these model parameters to update the cluster probabilities, and then we are using this cluster probabilities to update these model parameter in the maximization step. So and this we do iteratively because this algorithm gives a kind of guaranteed convergence. So after certain number of steps, we will find definitely that the instances are belonging to some clusters because the probabilities associated with that cluster are higher. So we can stop after, let's say, certain number of iterations. There are number of procedures to terminate the algorithm. So let's see, this is a standard algorithm. So we how we have converted it into the BSP framework using Apache HAMA. So in Apache HAMA, we write a super step. So this is one super step which does the expectation calculation, and this is another super step which does the kind of maximization calculation. And we have a barrier sink in place between the expectation as well as maximization. So in expectations, we have divided the input data into the n input instances. So each and every cluster node gets some amount of data. Expectation is really straightforward to do a kind of parallelize because we just need a model parameters for each and every node. So we have shared a model parameters between each and every node. So this cluster node uses this model parameters and does a kind of expectation step. And after the expectations, we need to communicate that to different nodes. So in maximization step, this is the kind of critical part of how we can parallelize the maximization step between different number of nodes. So here we can use at most a kind of the number of clusters into attributes, number of nodes. So let's say we in last example we have 3 clusters and we do have 2 attributes. So we can have a do the maximization step in parallel with 6 nodes, and we can just transfer the relevant data to each and every node, and there's the one node is responsible for calculating at least, so let's say one node is responsible for doing the processing for calculating the statistical models for at least one cluster attribute pair. So in case of high dimensional data, we do have a large number of dimensions, so we do have and if those the number of dimensions into the number of clusters to be found is greater than the number of nodes into the cluster, then we can achieve the 100% parallelization in the maximization step also. And we don't need to transfer data to each and every node, so there is very less data transfer also. So communication cost is also reduced. We need to do again a barrier synchronization, and this is the iterative approach, so we need to do this in this for multiple iterations. This is again a kind of we have expressed our algorithm where we do have some input and output, and we do have two super step, one for expectation and one for maximization. With our cluster configuration, we have done the experiments with 1, 2, 4, 8, and 16 number of nodes. We have used x86 quad core processors, which is each having 4 GB RAM, and we have used CentOS with JDK7. We have used two standard datasets from standard machine learning library. One is individual household electric power consumptions, which has 2 million instances and 9 dimensions. The another one is the data from YouTube multi-view video, which has 120K instances and 1 million dimensions. We have specifically chosen these two data sets because we want to have to see the results on the high dimensional data also. So in one case we do have a large number of instances, in other case we do have a large number of dimensions. So we see that results are with the HAMA are pretty positive. We see for with each and each one of these data sets we got a very good results as compared to both the standard Hadoop MR implementation as well as the Spark implementation. So time required to for each for both of these databases lesser than the we have done a kind of average time required by using our algorithm. This gives a kind of a scalability issue of our algorithm. We tried with the number of nodes. We changed the configuration of the cluster with 1, 2, 4, 8, and 16 number of nodes. So this is expectation cost, this is a maximization cost, and this is a communication cost. So you see as the number of nodes increase, in case of Hadoop, we get the communication cost gets tremendously increased. So, but in case of Apache Spark, we see there is still a kind of a good communication cost involved, but the maximization is negligible, as well as the expectation is somewhat constant going further. In case of Apache HAMA, we see a very negligible expectation maximization cost and only the sum amount of communication cost, which is again a very less. So we have a better results as compared to the Apache Spark on 16 node cluster. So we can say that Apache HAMA is also very useful framework, and in the context of distributing the compute intensive as well as data intensive kind of workload, it performs better than at least Apache Hadoop and with the Apache Spark also. And there are few reasons that we have depicted inside our paper, where we have given a kind of possible reasons why the Apache HAMA is a better framework for such kind of algorithms. So thank you. I hope if you have any questions, please write back to you on my mail. Thank you.